Okay, good afternoon, everybody. Welcome to the next edition of the Heidelberg Joint Astronomical Colloquium. First of all, can the virtual audience hear me? Please send a message saying yes or no. Okay, good. Thank you very much. Then I think we can begin. And this week we're making a small transition from looking at stellar matter disasters and their link to galaxy evolution to the sort of real cutting edge of galaxy evolution in a way which is this business of feedback. And we got the actual ideal person to think about that. This is Anna McLeod, and I'm going to hand over to Anna's host, Melanie Charance, to make the introduction.
Thank you. So yes, we have Anna McLeod this week. And Anna is an expert in stellar feedback in galaxies. She started already during her PhD, which she received in 2016 from ESO and the University of Munich. She continued then as a research associate in Christchurch, New Zealand, and a Masterton Fellow there, before moving to UC Berkeley in 2018, first as a postdoc, and then as a postdoc fellow, and then as a NASA Hubble Fellow in 2019. Since 2020, she's now an assistant professor at the Center for Extragalactic Astronomy in Durham, and she's going to talk today about connecting stellar feedback and the environment. Thank you very much, Anna, for being here today, and the floor is yours.
Thank you. Thank you so much. Can everybody hear me just fine? Yes? And also at home, just to make sure that the microphone is working? I hope that's a yes. Okay. Thank you so much for having me today. It's an honor to be here in this kind of setting. And I'm very much looking forward to sharing with you what I've been trying to work on over the past couple of years. Although, of course, with the pandemic and everything, it's been a bit challenging. So before I start, I wanted to say a couple of things. So first of all, if there is any question during the talk, please do feel free to stop me anytime. Just, you don't have to raise your hand like in school. Just shout, and we can have a small chat during the talk, and I'm not going to be offended whatsoever. The other thing that I wanted to mention is that some of you in this room, or perhaps also in the at-home audience, have seen versions of this talk over and over again, and so I apologize if that's the case. You can just zone out and think about something else if all of these slides are familiar to you. And then the last thing that I wanted to say is that I'm going to highlight a bit of work done by my students, Will Bowdery, Margarita Luna, and Lucy Rowland, and I just wanted to flash their names in case in the future you hear or you see them, just go and say hi to them. Okay, so that's, I think, all with the announcements. All right, so a brief outline of what I wanted to talk to you about today is the following. So yes, the theme is feedback from massive stars. So after a quick introduction and overview of what I mean when I say stellar feedback, I am then left with what used to be an entire section of slides on integral field spectroscopy, but over the years, that section has boiled down into one single slide. After those two general topics, I'm then going to move into a little more tangible scientific topics, which are somewhat a progression reflected in what my research career has been so far. So I started out as a PhD student working on Milky Way star-forming regions, and then as I progressed through my career, I branched out and I went further and further away. And now redshift is something that I use every day, and I didn't use that word very much at all during my PhD. All right, okay, and then if we have time, I hope that we will have time. I also have this little chapter about serendipitous discoveries, which is something that comes along with integral field spectroscopy data sets, as some of you might know. So let's see if we get there. All right. Without any further ado, feedback from massive stars. So what is it that I actually mean when I say feedback from massive stars? So feedback is this buzzword, this keyword, which we use, and what we really mean with that is the deposition of energy, momentum, and metals into the surrounding interstellar medium by the massive stars that have formed in those environments throughout their lifetimes, right? And just to be clear, massive stars is generally what we call everything over about 8 solar masses. Okay. Now, feedback is an umbrella term that encompasses a variety of different mechanisms via which the massive stars interact with their environment during their lifetime. So under that umbrella term, we have outflows and jets as these massive stars are still actively forming and accreting material. There is, of course, radiation pressure, ionization, stellar winds, and last but not least, supernovae. I'm not including in this list chemical enrichment, but it's definitely also a part of this umbrella term. I'm just not going to talk about it much at all in this talk. Okay. Oh, yes. Okay, and what I would like you to keep in mind is the fact that stellar feedback really is a multi-scale phenomenon, so it originates on the small scales of the individual feedback driving massive stars, but it really acts or has a profound impact on scales much larger than that, so up to the scales of entire galaxies. And because I don't have the fancy words, I'm going to use those of Sally Oy back in 1999, who said it perfectly. So on the scales ranging from parsecs to kiloparsecs, the relationship between the stellar and gaseous galactic components forms the basis of interpreting observations of galaxies and understanding their evolution and formation. All right, and just to drive the message home, what is it that stellar feedback actually does? Well, it can regulate at times how galaxies form stars and go through that life cycle of matter. Right, so stellar feedback, it enriches the interstellar medium with metals. It can drive the expansion of star-forming regions and disrupt molecular clouds. It regulates the formation of entire star clusters. It controls, therefore, the baryon cycle of galaxies. It can reshape the dark matter distribution in low-mass galaxies. And perhaps closer to home, it can dissipate protoplanetary disks. Okay? Great. So perhaps one key message from these introductory slides that I would like you to take home, if anything at all, is that without accounting for stellar feedback, really the simulated universe would not look like the observed universe. And here's perhaps a bit of a drastic example of this, but what I'm showing here on the left-hand side, my right, I'm direction blind, you should know. So my right-hand side is one of Phil Hopkins' older simulations where if you imagine feedback, stellar feedback being somewhat a button that you can turn up and down, okay, this button has been cranked all the way up to an extreme level, and what you observe is that the simulated galaxy really did not form many stars at all. Most of the gas is just sitting there doing nothing. Well, if you turn this button all the way down, so you shut off feedback completely, well then almost all of the gas reservoir of that galaxy is transformed into stars in what is almost a runaway process. Well, we know, of course, that real galaxies look like something in between, okay? And so this is my motivation to get up every morning and go to the office, is we need an observational quantification of these feedback mechanisms in order to get to that middle ground of the two extremes I just showed. Now, having said that, I think it's also fair to say, especially nowadays, since simulations and theory has made so much progress, it's fair to say that we do understand the physics of stellar feedback quite well, and simulations actually do a pretty good job at recovering observational properties, especially these global observational properties of galaxies as a whole, okay? But there are, of course, open questions, because otherwise we would not be writing grant proposals and observing proposals and whatnot. So for example, what we still don't really know is what role does the birth or galactic environment these massive stars form and play in the entire process? Or also, what is the role of the evolution of individual massive stars? Okay? So for example, hot topics that go towards these open questions are not all stars go supernova, some of them don't, and so we need to account for this fact in our models. But also, what is the contribution of so-called stripped stars to the global ionization budget, because these stripped stars emit ionizing photons at a much later stage than perhaps your regular O-type star. So what we really need is to improve our stellar evolution and population synthesis models, but also, and more importantly for today's talk, is an observational quantification of stellar feedback in different types of environments. Okay, so this is what the remainder of my talk is going to be about, the environmental dependence of stellar feedback. So in an effort, right, not only to understand this bottom-up sort of view of stellar feedback, but to turn the thing around and understand how the environment in turn affects how massive stars will feed back. Okay? Good. So I want to dwell on this point a little longer because I think it's very important to keep in mind for the rest of this talk. So the environment into which massive stars form in really sets the tone. Okay? So for example, it has been shown by Adam Ginsberg and his collaborators a while back that young massive stars, which are still forming, so these really young, massive young stellar objects, are able to heat their surrounding environment, the gas around them, out to substantial distances from the stars and up to substantial temperatures. Okay, and this is important because it has also been shown, and this is work by Sebastian Haidt, that it makes a difference if you let a star feed back into a cold neutral medium, or if you place the same star and let it feed back into a warm ionized medium. So a medium that has been perhaps prepped by some other feedback mechanism that came earlier, okay? Now I've boxed these in pink because usually we refer to all of what comes before supernovae as early stellar feedback, pre-supernova stellar feedback, okay? And that's important because we now know that pre-supernova feedback actually is pretty important. If you go to your favorite galaxy simulation, you probably, many of you in the room work on this, I don't, but rumor has it that supernovae have long thought to be the main source of stellar feedback in regulating the larger scale contribution of this in galaxies. But it turns out that without the pre-supernova feedback, or better, sorry, I'm going to rephrase this. The pre-supernova feedback sets the tone for what supernovae will do in turn when it's their time to deposit that energy and momentum into the medium. Okay. So to quantify this, what I want to call the feedback chain, and I know that John Bally refers to it as the feedback ladder in a more hierarchical structure, but I think feedback chain might be a more appropriate term. We need to know not only about the individual massive stars that are imparting the feedback, but also the environment the massive stars have formed in. Okay. It turns out that integral field spectroscopy is actually quite ideal to observationally study stellar feedback. The reason why this little section has boiled down to only one slide is because I don't think I have to introduce IFU spectroscopy that much anymore, because most people are now familiar with this technique, but just bear with me. Perhaps there are some people who are not super familiar with this. So integral field spectroscopy combines spectroscopy and imaging into one single instrument. So instead of having one single two-dimensional image, or one single spectrum for an object, you have a series of stacked two-dimensional images in which every pixel has a corresponding spectrum that spans the entire wavelength range covered by the instrument. So if you have an instrument with enough spatial resolution, you get, in the same observation, simultaneously, the photometry and spectroscopy of the feedback-driving stars. And you can also characterize the feedback-driven gas. Okay, this is highly convenient, of course. So you can identify and classify these massive stars. You can get the gas kinematics and gas properties. You can directly link or make that link between the gas and the stars and derive so-called feedback-related quantities. We're going to talk about that in a couple of slides. Thanks to what really is nowadays quite large spatial coverage offered by some of these instruments, we can do this for entire nearby galaxies. So, of course, we're all very familiar with the MUSE instrument on the Very Large Telescope, but by all means, it's not the only instrument that is useful in this field whatsoever. And I'm gonna get back to this at some point later in the talk. But I just wanted to mention MUSE because most of my work is based on MUSE observations. Okay, questions so far? No? All right. All right, so in that case, I'm going to go back in time quite a bit now in my sort of timeline, if you want. So this is work I started doing during my PhD. And the idea was, well, let's have a look at these curious pillar-shaped structures that, you know, are so famous and you can see on T-shirts and postcards and all sorts of other astronomical gift shop objects, because these structures are indeed shaped by and formed by stellar feedback. Right? So these pillars of molecular gas, we find them throughout star-forming regions, not only in the Milky Way, but also external galaxies. They are shaped into these pillar-like structures by the ionizing feedback and the stellar winds of nearby massive star clusters. All right? If you're interested in this, we can chat about it sometime later if you want. Just ask me and we'll get back to that. But the point is that they're not only being morphologically shaped, but they're also being destroyed by stellar feedback. They're being photo-evaporated by the impinging ionizing radiation. And so what we thought we would do is, well, let's sample pillars in different star-forming regions, so pillars that are exposed to different types of stars and star clusters, and see if we can somewhat quantify this effect of photoevaporation. Right, so that's what we did. We used MUSE to image a couple of these pillars, and it turns out that there's a tight correlation between the number of ionizing photons that hit the pillar tips, which are being photo-evaporated, and the mass loss rate of these pillars, okay? And this tells you that pillars that are exposed to more massive stars or more stars are being evaporated faster, right? Now, you can compare this to analytical models, for example, and within, you know, a factor of a few, the two agree pretty well. But this is only ionizing feedback. It's only ionizing feedback on small scales, and what is worse, it's only ionizing feedback on small scales in the Milky Way, okay? Really, what you would want is many, many more of these types of observations to properly statistically characterize stellar feedback. But unfortunately, the Milky Way is not the final frontier when it comes to these kind of feedback studies, and here's why. So first of all, the pillars of creation, you know, these famous pillars in the Eagle Nebula, I've boxed them right there with the field of view that we used with MUSE to image them, which was 9 MUSE pointings. It took about 4 hours of VLT time. So if you wanted to image the entire Eagle Nebula, well, it would take you, you can barely read it, about 180 hours of VLT time. And if you are an observer, you know that that's just a no-no. You can't do that, unfortunately. The other reason is, of course, MUSE is an optical instrument. We're in the Milky Way, sitting right in between all of the party happening out there. So, you know, we're just killed by extinction for most star-forming regions in the Milky Way. But perhaps the more interesting reason is that the Milky Way is just simply not representative of the vast galaxy diversity that is observed out there. Okay? So I want to get into this a little more. So the conditions across the universe, the environmental conditions, they differ across the universe and across cosmic time. So take, for example, metallicity, right? We know that the present-day universe is more metal-rich when compared to the high redshift universe. And this is taken from a numerical work, but of course, it's corroborated with observations. Now, metallicity, what does it do? Well, first of all, stellar winds are line-driven, so if you have less of that driving material, then of course you would expect lines to have less momentum transfer, and therefore you would expect weaker stellar winds at lower metallicities. Conversely, at lower metallicities, stars are hotter. They have higher photon fluxes, so naively you would expect higher radiation pressures at lower metallicities. So you want to quantify star formation and feedback under these different types of conditions, such as varying metallicity, for example. But of course, if you want to do this on a single star basis, then you can't do this at high redshifts or lower metallicities because you can't resolve individual stars or even individual star-forming regions, right? But what you can do is exploit metal-poor galaxies that are more nearby, like the Magellanic Clouds, for example, but are also other galaxies we're going to get into in a bit, to understand feedback at high redshifts. All right, but before I get into that, I realize that I haven't really talked about how to quantify stellar feedback yet. And so a very popular way to quantify feedback nowadays is via these so-called feedback-related pressure terms, which turns out that you can observationally calculate, okay, from your measurements, such as the direct radiation pressure, the dust process radiation pressure, the pressure from the ionized gas, and the pressure from stellar winds. Here's a beautiful example from Grace Olivier's 2020 paper, where she has taken observations of compact H2 regions in the Milky Way and calculated for each one of them these four pressure terms. And what she finds is that as a function of radius, of size of the star-forming region, okay, which is a proxy of their evolutionary stage, okay, younger regions, older regions, there is a turnaround in which feedback mechanism is dominant. So the younger regions are dominated by the dust process radiation pressure, the red data points there, okay? And then as the regions expand and evolve, that particular feedback type is not dominant anymore, and what becomes dominant is the pressure from the ionized gas and stellar winds instead. Okay? But there's an additional complication to this plot, which is the following. These data points down here are not Milky Way data points. These are measurements in the large and small Magellanic Cloud. So these are drastically different types of environments. We're now at lower metallicities, lower dust content, different type of host galaxy, and so on and so forth. So we want to understand this additional form of complexity introduced by putting the same, or putting data points of different environments on the same plot. Another nice example that goes towards showing the same point is this work by Ash Barnes of feedback-related pressure terms in the central molecular zone. And again, here Ash plots, let's see if that, plots the LMC and SMC data points, which have first been published by Laura Lopez back in 2014. And these are the same data points plotted here in Grace's work and in Ash's work, just to show, again, this trend where with evolutionary stage, there's somewhat a swap in which pressure term becomes dominant. Okay? No, other way. All right. So assuming now that we know that the environment plays a crucial role at regulating feedback, let's take, for example, a closer look at the direct radiation pressure as a function of metallicity, for example. Now, this is the exact same data points of the previous slide, so the LMC and the SMC, and Ashbarn's, sorry, I keep on pressing the wrong button, Ashbarn's central molecular zone data points, and I've just naively plotted these assuming one single metallicity value for all of them. But already your eye is somewhat guided into thinking, well, at the very high metallicities and high dust content of the central molecular zone, the direct radiation pressure is significantly higher than at low metallicity environments. And it actually makes sense if you think about it, right? So at lower metallicities, you have this lower dust content, which means that you have lower direct radiation pressures. Why? Well, because there simply is less stuff to impart momentum to. But really what you would want to do is populate this plot. And I don't mean only put more data points in this particular region, but we know of more metal poor, like a lot more lower metallicity environments. And so you would want to expand this plot going down below a gas phase abundance, in this case, of 8. All right. Good. Staying in the Magellanic Clouds, these are now again Muse observations of two giant star-forming complexes in the LMC, N44 and N180, if you know your phone numbers in the LMC. And the reason I'm showing you this is because I want to take now a step back again and try and connect those individual feedback driving massive stars with the environment that they're affecting, okay? So we used 15 hours of VLT time to get pretty massive mosaics. So these are 64 pointing mosaics each of these two regions. It's about 128 data cubes, give or take, because some of them were not great. Of course, this gives us access to thousands of individual stars. Of course, not all of them are massive stars, but you get the point. And probably more spectra than is healthy for anybody. And so with this work, what we wanted really to do was to get a full picture of the stellar and gaseous content of these two regions. So we covered in total 11 H2 regions, individual H2 regions, spanning radii from 3 to 40 parsec. We were able to resolve the feedback driving stellar population, so to identify and classify those massive stars. We actually got 10 new detections of O-type stars in these two regions alone, which, to be fair, are quite well studied. And we were able to do the whole suite of gas kinematics and gas property observations. So just to drive the message home, this gives you the simultaneous, or the ability to simultaneously characterize these two players in what is stellar feedback. And one of the questions that we wanted to answer with this data set was, well, so how does the photon flux a given star or stellar population emits during its lifetime translate to the H-alpha luminosity which we observe from the gas, right? Because, of course, not all of the photons a star emits will go into producing said H-alpha luminosity. Some of the photons will escape. Some of them will be absorbed and then re-emitted and then perhaps reabsorbed, and so on and so forth, okay? So what we find is that there is a pretty high degree of photon leakage. So the stellar populations that are emitting these photons are less efficient at producing that observed H-alpha luminosity when compared to a standard case B recombination. So this is just the standard way, the Kennicott and Evans, Kennicott and Evans way of just translating an observed H-alpha luminosity to an inferred photon input from the underlying massive stellar population. All right, but perhaps more importantly, the other question we wanted to answer is, in the spirit of what I've shown you previously, which feedback mechanisms are dominant in these regions? And what we find, very much consistent with what I've been showing you previously, is that these H2 regions, or their expansion, perhaps better, is dominated or mainly driven by stellar winds and a warm ionized gas. So no big surprise there. These are fairly evolved regions. Okay, they're not ultra compact like the ones Grace Olivier was working on. So it's not a huge surprise. Okay. But then again, these are only 11 H2 regions in the LMC. And this does not help us, again, understand how feedback might depend on the environment. So for example, again, metallicity and location within the host galaxy. Just to flash this young lady up here, this is Eve, one of my former master's students. She has sadly left academia now because of a variety of reasons, but she did really amazing work and performing a very similar study in the small Magellanic Cloud, so at even lower metallicities than the LMC. And hopefully we'll get this published before she completely leaves us. All right. But the SMC and the LMC are, again, not the final frontier when it comes to feedback studies. And the argument is very similar to what I was trying to make earlier, okay? Instead of tens of regions with this level of detail, you really want to have hundreds, or perhaps be bold, thousands, to statistically characterize feedback. So this is 30 Doradus, boxed here, approximately 40 arc minutes on the side, and if you wanted to use MUSE to image 30 Doradus, it would require about 200 hours of telescope time. Again, you can't do that. Also, it really doesn't tell you anything about the environmental dependence, because you don't have the sampling of different galaxy properties or location within galaxies, and so on and so forth. So really what you want to do, and here we're getting to the juice of things, is to survey nearby galaxies, so beyond the Magellanic Clouds, with integral field instruments. Okay, and at this point, many of you might argue, if you go beyond a certain distance, you're probably not going to be able to resolve single stars anymore, which is a very fair point. And I completely agree with, there is a certain distance at which you can't do this anymore. But we can push single star studies nowadays to megaparsec distances. And that is because we have access to high spatial resolution imaging from, for example, HST, but then, of course, also coming up in the near future, James Webb. You can definitely tell that in this particular comparison, the HST image has individual stars which merge into bright blobs in the MUSE, in the corresponding MUSE image. And so what you do is you exploit this high spatial resolution HST data to perform better at fitting the PSF, and therefore obtaining what is really an enhanced spectral extraction at these large distances, or in crowded fields, which is where this technique was first applied in, or used for, such as, for example, globular clusters. Right, and so this will allow you to identify and classify stars up to megaparsec distances. In this case, NGC 300, which is at about 2 megaparsec. And the good news is that HST has covered a whole lot of these nearby galaxies. So, for example, surveys like Angst and Legis is there anybody in the room who knows exactly how many galaxies are combined in these two surveys? I don't know, but must be close to 100. Yeah, good. And also, and I probably don't have to tell you this because this is, where FANGS is strong, but there are, of course, nearby galaxy IFU surveys that, like FANGS or Signals, also covering these same galaxies with MUSE or other integral field units. All right. But before we talk about those, let's talk about NGC 300 some more, because I like it very much. It's a beautiful galaxy, which we imaged with a total of 35 MUSE pointings into a really nice mosaic covering the central part of the galaxy. You can see that shaded there or boxed in blue. together with that, from the ANG survey, we also have almost co-spatial HST coverage, and also a very nice ALMA data set, which was used in Diederik's work back in 2019, which I can't talk about today, but you certainly all know about. All right, this is the ionized gas image from the MUSE data in its full glory, and I don't know if it's maybe a bit dark or not, flashy enough, but it's actually a really massive data set. So this little pink dot here is the nuclear star cluster of NGC 300, and you can somewhat, with these bright blobs, which most of them are H2 regions, you can trace the spiral arm structure just by looking at where these blobs are and line up. You see some of them are more green, others are more blue, and some of them are smaller, some of them are bigger. These are not all star-forming regions. Some of them are planetary nebulae, others are supernova remnants, and then there's stuff in there that we still not know what it is, to be honest. We can talk about some more of that later as well if you want to. But what we first did was we wanted to showcase that we can actually do this trick of identifying and classifying massive stars at the distance of 2 megaparsec, which is NGC 300. So we picked 2 of the largest H2 region complexes and tried to demonstrate this technique. Okay, so this is in white now, the NGC 300 footprint that we have with MUSE, and we're just focusing on this little section here and the 5 in total individual H2 regions within them. Right, so again, NGC 300 is a pretty well-studied galaxy, but in these particular regions, no O-type stars were previously known. And with this enhanced spectral extraction technique, we were able to identify 13 O-type stars and 4 Wolf-Rayet stars in this initial study of the five regions. So I'm just going to flick through this in the interest of time, but here are just a couple of spectra of these O-type stars cropped to the region of the helium-2 absorption line, which is a telltale signature for O-type stars. And that pink there is just a model atmosphere fitted to it. You can see the drastic difference again between the resolution of HST and MUSE at this distance, right? Here is just an example of a Wolf-Rayet star, and then you can calculate your favorite feedback-related pressure terms and have a look at, for example, what they contribute towards the star formation rate of these regions. But I don't want to go into this at all. I just want to say that this is possible. Right? It's possible to identify massive stars at these distances, and therefore these detailed feedback studies are feasible in nearby galaxies. And my PhD student, Will, is now working on an automated identification and classification algorithm using the NGC 300 data set, so stay tuned for that. Hopefully it will be published soon. But also to try and understand what then we can learn from that in terms of unresolved studies. Yeah?
What were the hot stars, the massive stars missing the HST photometer?
Sorry, say again?
Why they were not looked up by the HST photometer?
Oh, they were. The stars, they were. But you can't get a spectral type from the HST photometry alone. Yeah. Okay. Sorry if that was not clear. Okay. All right, so there's a significant effort to map the nearby universe with integral field units by the late 2020s. And here's a general shopping list of some of these. Okay, so there's of course LVM, and so Catherine is probably somewhere. Oh yes, there she is. Hello. Which will amazingly cover both the LMC and the SMC with a contiguous IFU spatial coverage. And I'm really looking forward to that. So this is something that you, of course, as I talked about earlier, you cannot do with PI-driven proposals, and LVM is going to do it for us. Fangs is, of course, something that needs to be in this list, as is signals. Signals is complementary to Fangs very much. It uses an integral field spectrograph, a Fourier transform integral field spectrograph, for those of you who are interested in instrumentation on the CFHT, Hawaii. And together, I think they have by now observed about 60 nearby galaxies, perhaps a bit more. There's, of course, NIRSPEC and MIRI on James Webb. KMOS on the VLT is the underdog of the near-infrared IFUs, but a brilliant instrument. There's going to be GMOS for Gemini. This is an instrument that has now been approved and is in development. There is Keck with KCWI, and I've heard that KCWI, for those of you, again, who are familiar with this instrument, so KCWI is very similar to MUSE, but it has a more restricted wavelength range. It doesn't go as far to the red at all, but it goes bluer, which is very important when you are trying to study massive stars. But it's now being upgraded to also include a redder wavelength coverage. So I'm hugely excited about that. And then, of course, all the future 30-meter plus class telescopes will have IFUs as their flagship instruments. So really, it will be an endless playground once all of this is going to become available or is going to see first light. Okay, so now beyond a few megaparsec, we can't obviously distinguish individual stars anymore. But we can still do feedback studies, right, of integrated properties of H2 regions. So this is now, of course, beautiful work by Catherine, where she has made these incredible metallicity gradients for an initial set of the Fangs galaxies. And I say incredible because each data point on these plots is now an individual H2 region in a galaxy. And so there are many, many of these data points. And this is hugely exciting because this now allows us to study feedback as a function of environment, for example, metallicity, using data from many more star-forming regions than was previously possible. Okay? And going forward, these kind of surveys will also allow us to study feedback and its dependencies on things like the properties of the host galaxy. So is it what kind of mass does this galaxy have? Is it interacting? Is it merging? Does it have bars, spiral arms, and so on and so forth? But I want to get back to NGC 300 just for a sec, okay, and talk about these non-resolved star studies, but more integrated properties studies for a sec. All right, that was too quick. Okay, so again, this is our 35 MUSE, pointing MUSE mosaic. And what we did was, wrong button again, we extracted integrated spectra of all the H2 regions that we could identify in this image, which is about 100 regions. And we constructed the radial abundance gradient for this galaxy, which is pretty much consistent with what the literature already knew. Just for comparison, this is Milky Way, LMC, and SMC metallicity just shown there for you. But what we wanted to know is there a variation in these feedback-related pressure terms that quantify feedback as a function of environment, as a function of, say, metallicity, for example? And so this is what I'm showing you here. This is now not as a function of metallicity, but as a function of radius, so galactocentric radius, which traces the metallicity gradient. Metallicity is color-coded, and the red to purple data points are the direct radiation pressure, and the greenish-bluish data points are now the pressure of the ionized gas. And so you see very weak trends there. And I emphasize that these are weak trends, okay? Which seem to indicate that as the farther you go out in the galaxy, so the lower the metallicity, the higher these pressure terms become, okay? And this might be counterintuitive, especially for the direct radiation pressure, because if you don't look at this for a sec and just think about it, what I said earlier was at lower metallicities, you have lower dust contents, and so the direct radiation pressure should actually decrease, not increase, okay? But as it turns out, NGC 300 is a bit of a special child, because exactly in that portion of the galaxy that we're covering with the MUSE data, the dust mass surface density is actually ever so slightly increasing, despite the metallicity decreasing. And so because you have that enhanced dust content, you have more stuff to impart momentum to, and so it kind of makes sense that the direct radiation pressure increases. But why am I telling you this? I'm telling you this because if you think back to the beginning of my talk when I was talking about early pre-supernova stellar feedback and what it does to prep the regions for when supernovae go off, well, we had a look at what this scenario means in terms of the environment supernovae will explode into. So we cover a huge number, 7 supernova remnants with this MUSE data set. Granted, it's not a large sample to do proper statistics with, but what it seems like is that if you calculate the density, the pre-supernova density, so this is the density of the ISM the supernova has exploded into, not the measured density, the current one, but what is inferred, what you see is that supernovae at larger galactocentric distances, so at lower metallicities, have exploded into a less dense environment. Why? Because there the pre-supernova feedback was increased. So early stellar feedback has this profound effect on the conditions into which supernovae will then feed back into. So where stellar feedback is enhanced, again, supernovae explode into these lower density environments, hence affecting how supernovae will feed back themselves. Okay. Now, what now, though, at much lower metallicities? So I want you to quickly look at this plot again, which I showed earlier, where we have the central molecular zone data points, and then the SMC, the LMC, and the SMC here. And what my student Lucy has been doing is she's been quantifying stellar feedback in nearby dwarf starburst galaxies, so at much lower metallicities, and you can see, you can tell just by looking at the gas phase abundance that is now plotted on this plot and compared to this other one. So she's really extending these kind of studies to much, much lower metallicities. And what she finds is that there is a clear dependence on metallicity of the direct radiation pressure. So these are these data points down here. This is not her work. This is work done by Ash Barnes and for the FANGS galaxies. But as you go down to those lower metallicities, the trend is consistent. You have lower direct radiation pressures. It's less clear what the pressure of the ionized gas is, but I don't want to get into that can of worms too much for now, as it's very preliminary. Okay. Now, completely different topic, but yet somewhat still related, is going back to the connection between simulations and observations. So I've showed you all of these nice observations, but at some point, what you want to do is use these to inform simulations. So what my student Margarita has been doing is she's been making mock IFU data cubes from, in this case, Eagle simulations, and trying to understand how different prescriptions of stellar feedback affect these dwarf galaxies in this case. Okay, so what she's doing is she's selecting Eagle dwarf galaxies, running them through a tool called SimSpin, which produces synthetic MUSE cubes. And then she treats these MUSE cubes in just the same way as an observer would to extract observable quantities. So she's, for now, been using this very nice tool called the GIST pipeline, which gives you, or which spits out, given it a MUSE cube, stellar kinematic, ages, and metallicities. And it works just as well on these synthetic IFU cubes as for what it was originally designed for, which is real MUSE cubes. Okay? With the question in mind, what does the change in the prescription of star formation do? So, and as a consequence, what does the change of stellar feedback do to things like the dark matter or the baryonic properties of these galaxies? as traced by the stellar kinematics. And this is very, very preliminary work, but as you, let's see, okay, I've arranged this in a slightly different way to a previous version of the slide, so bear with me. Now, this is the direct output of this GIST pipeline for 2 different galaxies. So this is the same galaxy simulated with 1 prescription of stellar feedback and then a slightly different prescription for stellar feedback, okay? And there are clear differences in the results of changing this prescription. The first galaxy, which forms stars much more easily, has a clear sign of rotation in its stellar disk. You can see it has formed stars at a somewhat light time step in the simulation in the center. So this is where the youngest stellar population is located at, and therefore where it's most enriched. While the bottom row here is somewhat much more unclear. Again, I don't want to go into too much detail here, first of all because I'm running out of time, but also because it's very preliminary work. But do keep an eye out on the archive in the next couple of months because Margarita is writing this up. Okay, so stay tuned for Margarita propagating this to the full Eagle cosmological volume, but also making the connections between stars and gas, and producing not only MUSE data cubes, but for different IFUs, but also using different types of simulations. Okay, we're there. We're there at the end. I can see some people nodding off, so I'm just gonna go quickly through this. All right. So I hope that I somewhat managed to convince you that feedback from massive stars does matter, and that we need to quantify it in terms of observations. And the best way of really getting a big picture out of this is by quantifying feedback in different types of environments. Why? Because the environment matters. Integral field spectroscopy is ideal to do this, and first results towards this observational quantification are promising. Now, there is a definite need to expand this type of work to an even greater diversity of environments. I didn't go into this a whole lot at all, but it goes towards what Margarita is doing. There is a definite need to compare observations and simulations and make that connection between the two. And the way that you should do this is by treating the mock observations the same way as you would your real observations. Okay, thank you very much for your attention. I will take questions now if there are any.
Thank you very much, Anna. A very detailed overview of the current observational situation on what is a physically very complex thing, and obviously you're making some progress to distinguish between these different forms of feedback. I'll open the floor here for questions, and if the audience, the virtual audience, would like either to put their hand up or to type a question in to the chat, we'll come to you forthwith. So, first of all, questions here. Just while you're thinking about that. Actually, while you're thinking, I have a question about the ionizing radiation feedback. I think earlier on you were looking at star formation regions, and you mentioned that quite a lot of the ionizing radiation was escaping. So what sort of percentage was that in that case? Was that imaginary clouds that
Yeah, that's
work?
right. So typical values range between, I want to say, 40 and 60%. But you know, certainly there are higher and lower values than that. But that's about the range of escape fractions.
Okay, Diederik, thank you. Thank you, that's interesting. I'll come back to you later. That's a huge number, Diederik. Sorry. No, you won't get on the recording.
Okay. Really cool talk, Anna. Thank you. So I have a question about the pressure terms as a function of metallicity, where you show the LMC and the SMC, and on the right, the central molecular zone. Because I noticed that the metallicity dynamic range on the x-axis is actually quite small. It's less than an order of magnitude. But then the dynamic range in the pressure is more than 4 orders of magnitude. And that kind of made me think, because I thought, like, it's kind of weird that that would be purely a metallicity effect.
Oh, yes, okay.
And it turns out that, you know, in the central molecular zone, it turns out the actual midplane gas pressure is actually 4 orders of magnitude higher.
Yeah.
And that sort of makes me think, okay, maybe there's actually a form of self-regulation where the feedback just delivers the pressure it needs in order to disrupt the surrounding ISM and actually stop the star formation. So it'll keep forming stars until it can actually blow up the surrounding environment,
Right.
and then it would not be a metallicity effect. So
Yes.
my question is, because that will happen everywhere, is how are you going to actually distinguish between the metallicity axis and all the other axes of other relevant quantities that are changing as a function of environment?
Right. No, that's an excellent question. And I do realize that I perhaps sold it as being metallicity only cause that is you know, responsible for that trend. But you're very much right. There are a number of factors that we have not yet been able to consider, given the observations that we have, but dearly do need to consider. And you know, dynamical situations that are more complicated than the ones you have, for example, in the Magellanic Cloud, such as are in the CMZ, are certainly worthwhile looking into. And I just wish we had all of the data in the world to do this, but it's a very fair point. And I wish I had a proper answer as to, you know, what we need to do or what we need in order to do this, but I don't have it yet.
Let's talk over dinner.
That's fine.
Okay, yeah, dinner later. We have already a question from the virtual audience, so I invite Ralph Klesen to pose his question. Please go ahead, Ralph.
Hello, can you hear me?
We can't hear you.
Okay, excellent. Thanks, Anna, for this very nice talk and presentation. You pointed out that local feedback matters a lot, right? Early feedback is in this category. So I'm wondering about the Eagle post-processing with its relatively coarse resolution, where you will not resolve the ionization structure around individual star clusters very well. How realistic will these simulations be? And are there some pathways to use subgrid models to improve on that? What is your take on that?
Hybrid A. Okay, yes, much better. All right, so I'm an observer. I'm definitely not somebody who runs any of these simulations, but what we do need is to not only make the connection between simulations and observations, but make the connection between resolved simulations of individual star-forming molecular clouds and larger scale simulations of entire galaxies, or perhaps even on a cosmological scale. But I suppose that you yourself are much better qualified to address this. So the pathway should be twofold between the connection of simulations and observations on these small scales. The connection between small-scale small-scale simulations, or if you want subgrid models, and the larger unresolved scales. And I said twofold, but I want to add a third complexity here, which is using resolved observations to infer what our limitations are when we don't have the luxury of these high spatial resolutions at perhaps higher redshifts. Although I'm not sure that I fully got all of your question, because you did cut out at some point.
No, I think you cut it. I mean, in the end, I think it's extremely complex, and it's a multi-year project to combine small scales and large scales, both in the modeling side and in the observational side. So thanks.
Thank you. We have a question at the back.
Thanks. Well, I think it's on. Oh, okay. Yeah. Okay. Okay, maybe this is a naive question, but I do not understand why there are so like, actually there is just 1 point for the metallicity of the Milky Way, right?
Sorry, you have to speak up. I
There is, I think this is maybe a naive question, but why we don't have more points for the Milky Way if we know that there is a radial metallicity gradient through the galaxy?
No, you're absolutely right. So that one plot that I was showing is a very dirty plot. Okay, so those red data points from Ash's work are all in the central molecular zone. So I've naively just assumed one single metallicity for all of them, which I think is a fair representation. But of course, the Milky Way has its own metallicity gradient. But I think it's okay to use just one metallicity value for those particular ultra-compact H2 regions, which are all in the central molecular zone within, I don't know, a couple of hundred parsec from each other. Does that make sense? Yeah.
Okay, thanks. One question at the front. Microphone close to the mouth.
Okay. So actually I have two questions. The first one is like, how do you define the pressure? I mean, radiation pressure and the stellar wind pressure.
The pressure terms?
Yeah, how do you measure it?
Okay. Anyone in particular, or?
I mean, the ionized gas pressure and the stellar wind pressure.
Okay,
yeah.
So I think I do have perhaps a backup slide for that. Let me just quickly see if I can. Where's my mouse? I can't go on. Let's just do it like so. Nope. All right, never mind. Something. Oh, here it is. I can just hit this button again. Okay. So the direct radiation pressure. I have to. It's a bit convoluted because there are different ways of doing it depending on what you want to learn. But the direct radiation pressure has a luminosity term at the top, and then folded into that is the radius of the region. So what I'm showing you here is actually the photon flux inferred from the stellar population, but then, because you have escape fractions and so on and so forth, not all of those photons will go into producing the H-alpha luminosity. So a better way of calculating the direct radiation pressure would indeed be to use the H-alpha luminosity transformed into bolometric luminosity for that. The pressure of the ionized gas is simply coming from an ideal gas argument. And so for that, we conveniently cover the sulfur lines with the Muse data, so we get an estimate of the electron density, which then translates into a pressure term like that. And then we have stellar winds too, but I haven't talked about that too much, so I'm inclined to just leave it out.
Okay, then the second question is about the simulations. So do you only put the stellar feedback or the supernova feedback, this kind of stuff?
So
in the
which
simulation?
simulations are you talking? Are you referring to?
In the Nature paper, I mean.
Was it the Eagle simulations?
Yeah.
So Eagle simulations are cosmological runs, right? So these are completely unresolved. So there is like a prescription for feedback, which is mainly supernova feedback. Yeah.
But for the latter several slides, I mean, in the last few slides, you also mentioned the feedback on the galaxy evolution, right? The simulation result in the, I think it's.
I think that was what I had. Oh, I don't know. I'm confused now. That was Eagle.
Yeah.
Yeah.
Okay.
Yeah. Sorry, I'm just trying to remember. Did I mention anything else? I don't think so for
Okay.
now. But we will look. But we will definitely look into simulations that have the resolution to actually disentangle different types of stellar feedback for sure.
Okay, I think we just have time for one, possibly two more questions.
Yeah, hi, great talk, thanks. It's going to be probably a simple question because I work on completely different things. You mentioned these beautiful pillars at the beginning of your talk and how they are eroded by the radiation of the nearby stars. And I can see how this should work. It makes a lot of sense to me. What I do not understand is how do you measure, there was a scaling relation between the flux of photons and essentially the erosion rate. How do you measure this mass loss rate observationally?
Okay, so the observations of these Milky Way pillar-like structures are at a high enough spatial resolution that you can actually disentangle the photoevaporative flow from the actual pillar material. So we resolve that off-flowing material. It has a density, and it has a velocity, and it has its own emission. Okay, so from that, and then assuming some geometry for the tip of the pillar, which we just assume is essentially just a spherical cap, it gives you how much matter is actually streaming away from the pillar. And then for the ionizing photon flux, these are all pillars around very well-studied clusters where we know exactly how many types, how many massive stars of what spectral type are in them. And so we can just translate that spectral type to a photon flux, which is what is on the x-axis. Yeah.
Okay, and now I think we just have one more question.
You have a very nice slide up here explaining the pressures, but I'm worried about the X-ray emitting gas produced by the supernovae, which in these older, larger, giant H2 regions is probably going to start becoming important.
So, sorry, is your question why that is not up here?
Essentially,
oh, okay.
Or how do you treat it?
Oh, I see, okay. Well, yes, very good question. It's not up here because this particular slide is, again, one of these reused slides from previous talks, where I was mainly talking about the work we did in the LMC, and we did not have any information about the X-ray emitting gas whatsoever at that stage. But of course, if you did have, then you would want to include that too. In fact, Laura Lopez and her now former student is exactly what they were doing. So they have deep X-ray observations, mainly from Chandra, and yes, that's how you would fold that in, for sure.
Okay, well, thank you. I think that's all we have time for. Anna will be here until sometime tomorrow morning, I believe, right?
Yes, that's right. I have to leave around lunchtime.
If you have any more questions, then contact Anna direct or Melanie, her host, and you'll be able to have another chat if you have more thoughts about this very interesting colloquium. Before we thank Anna, I'd like to make two announcements. First is next week's colloquium, where we will welcome Beata Stelzer to tell us about active stars, sort of ingenious multi-wavelength type of analysis. Let us just give Anna a great send-off for what has been a very interesting symposium on a fast-developing topic, observationally driven, and let's hope that in the next decade we get closure between theory and observations, and Anna will no doubt play a great part in that. So thank you very much, Anna.